around its own axis in a particular direction, this direction, either clockwise or anti-clockwise direction, then it will possess one overall magnetic spin, and similarly the overall magnetic spin having the same direction as that of the magnetic moment. We can get the relationship between the magnitude of magnetic moment, that is magnitude of magnetic moments means modulus of mu, and spin angular momentum quantum number by substituting the value of magnitude of spin angular momentum in equation 2 and 1. So here equation 2, mu equals to gne divided by 2m into I, and equation 1 is I equals to square root of magnitude of I equals to square root of 1 whole into I plus 1 into h cross. So if we put this value, and here in the equation 2, that is mu equals to gne by 2m into I. So if we put the value of I from equation 1 in equation 2, we can write magnitude of mu equals to gne by 2 mp. mp stands for mass of proton, into square root of I into I plus 1 h cross. And here, so this is one constant value. E is that is the charge of the proton, that is constant. H cross is constant. Mass of the proton is constant. So all these terms E into H cross by 2 mp, that is a constant value, that is called nuclear Bohr magneton. So that is called mu n, and hence the formula will be magnitude of mu, that is magnitude of angular momentum, magnitude of spin angular momentum, magnitude of mu equals to gn mu n into square root of I whole into I plus 1. Now in the question, which of the following nuclei having magnetic moment and will be NMR active? So in order to NMR active, the I should not equals to 0. That means where the molecule where I equals to 0, that is NMR inactive. So according to the first one, you can find out from this question which is having I equals to 0. So if I equals to 0, that is NMR inactive, and if I is non-zero, that is NMR active. Now coming to quantization. So all the nuclei having non-zero spin angular momentum, that means I is not equals to 0, are associated with magnetic moment, and hence may be assumed to be behaving a small bar magnet. However, you must remember that the nuclear spin of the magnets of a quantum particle, unlike a bar magnet, and hence may take up only certain allowed orientation. A nucleus with spin quantum number I, when placed in an, that means if the nucleus I is not equals to 0, and if the nucleus will be placed in an external magnetic field, it can assume that it will have 2I plus 1 orientations. For example, if a nucleus having I equals to half, then the number of orientations equals to 2I plus 1, that is 2 into half plus 1, that is equal to 1 plus 1, 2. So it will possess 2 orientations. So the 2 orientation, that is the Z component of the spin angular momentum Iz, is quantized, and its value in the direction of the applied magnetic field is given as Iz equals to Mi h cross, where Mi is the quantum number of the Z component of the spin angular momentum, and it takes the value minus I to 0 to plus I, and the possible orientation for I equals to plus half and minus half. So here I equals to half means it will have plus half. So this is the orientation for plus half, and this type of orientation for minus half. So it will have two possible directions, two possible orientations. The possible orientation of nuclear spin with I equals to half in the applied magnetic field B naught. So if the applied magnetic field will be B naught, and if the nucleus if in the nucleus I equals to half, it will have two possible directions, two possible orientations. One orientation associated with Mi equals to plus half, and another orientation associated with Mi equals to minus half, both having same magnitude. So you can see that the orientation of the nucleus with spin equals to half is either aligned parallel or anti-parallel to the applied magnetic field. Now this is the direction of applied magnetic field. This one is the direction of applied magnetic field B naught, and from this figure you can observe that either it will align with the direction of applied magnetic field, or align means align parallel or align anti-parallel. That means in opposite to the external magnetic field. So any other orientation for the nucleus is not possible or permissible. As the value of I equals to half, according to this formula, 2I plus 1, it will possess two orientations. One orientation will align parallel to the applied magnetic field, and another orientation will align anti-parallel to the applied magnetic field. No other type of orientation will be possible for this type of nucleus. Similarly, if the value of I equals to 1 or 3 by 2 or 2, then the number of, if the value of I equals to 1, then the possible orientation equals to 2I plus 1, 2I plus 1, the value of I equals to 1, so the possible orientation will be 3, so it will possess 3 different orientations. And if the value of I equals to 3 by 2, then the possible orientation will be 4, and if the value of I equals to 2, then the possible orientations will be 5 respectively. The different orientation of the nuclear magnetic moment for the nuclei are associated with different energies, and the energy equals to minus Mi Gn mu Bi, B naught, where B naught is the strength of the applied external magnetic field. And the two orientations, if I equals to half, the two orientations associated with the two orientation, that means the anti-parallel and parallel orientation, that means the two orientation associated with two different form of energy. So if that will oriented in parallel to the applied external magnetic field, then its energy will be increased. So that will possess Eb equals to half Gn mu n B naught. And similarly, if that will anti-parallel to the applied, sorry, if that will anti-parallel to the applied magnetic field B naught, then its energy will increase, and the value of the energy, that is called E beta state, that is called beta state, having anti-parallel alignment with the applied external magnetic field B naught. So in that case, Mi equals to minus half. So putting the value of Mi equals to minus half, we can write E beta equals to half Gn mu n B naught. And similarly, putting the value, if the spin will be parallel to the aligned parallel to the applied external magnetic field B naught, then it will be sort of more stable state and having lower energy. And here Mi equals to plus half, that is the alpha state, and here the energy of the alpha state E alpha equals to minus half Gn mu n B naught. So the energy levels with M equals to half, that is with parallel spin to the applied magnetic field, is denoted as alpha and sometimes described as spin off. And if the state with Mi equals to minus half, that is denoted as beta, and that is described as spin down. For the nuclei under observation, it is the alpha state, which is the state having lower energy, and the beta state having higher energy. the energy of the alpha state E alpha equals to minus half Gn mu n B naught, and the energy of the beta state equals to half or plus half Gn mu n B naught, and the energy difference between the two states equals to half Gn mu n B naught, that is the beta state, minus energy of the alpha state, that is minus half Gn mu n B naught. So which is equal to, so that will become plus, because minus of minus, that will become plus, which is equal to Gn mu n B naught. This implies that the frequency of the radiation required, because we know that E equals to h nu. So this is the value of the energy difference between the two states. One is spin up and another one is spin down state. So for the energy difference between the two states equals to Gn mu n B naught, and this much amount of energy is required for flipping of the nucleus between the two steps. This implies that the frequency of the radiation required, which is equals to, because we know that del E equals to h nu, and the frequency of the radiation required for a transition from the lower spin state to the upper spin state equals to h nu equals to del E, or nu equals to del E divided by h, and we have calculated the value of del E, Gn mu n B naught. So Gn mu n, so mu equals to, nu equals to, frequency equals to Gn mu n B naught divided by h. And for the magnetic field used in NMR instrument, this frequency falls in the radio frequency region of the spectrum. So after calculating the value of nu or frequency, you will observe that, and putting the value of magnetic field mu n Gn, and putting the value of Planck's quantum number, you can see that for magnetic field used in the NMR instrument, the frequency nu falls in the radio frequency region of the spectrum. In other words, a suitable radio frequency radiation can bring about transition from alpha to beta spin state. So if a suitable radio frequency will be irradiated to the nucleus, it is possible to transit from the alpha state to the beta state. Now coming to the population of energy levels. When placed in an external magnetic field, all the spin magnetic moments in the sample do not occupy the lowest available energy states. So if you apply external magnetic field to any type of sample, you will observe that all the spin magnetic moment of the sample do not occupy the lower state. So the number of that is the population of the different energy levels will be governed by Boltzmann distribution law. Now according to the Boltzmann distribution law, the number of spins in the lower state, that is n to upper, divided by number of spins in the the number of spins in the upper energy state, that is n to upper, divided by number of spins in the lower energy state, that is n1 lower, equals to e to the power minus del E by kt. So this is according to Boltzmann distribution law. Here del E is the energy difference between the two levels alpha and beta, and k is the Boltzmann constant having value 1.38 into 10 to the power minus 23 joule per Kelvin. As the energy difference between the two spin states is very small, the upper level will always be appreciably populated at all temperatures above absolute zero. And again, as the energy difference between the two states is very small, because here the frequency of the radiation falls in the radio frequency region, and its wavelength is extremely high, so its frequency value will be less, and hence corresponding E equals to h nu having very small energy. As the energy difference between the two states is very small, it will observe that the upper energy will be appreciably populated at all temperature above 0 Kelvin. Now let us calculate the ratio of the protons with magnetic. So here we are taking the example of 1H1, that is proton, PMR. Now let us calculate the ratio of the protons in the magnitude in a magnetic field of 1.5 Tesla at room temperature means 300 Kelvin. So here we can calculate the value of del E equals to Gn mu n B naught. So we know that for proton the value of Gn is 5.585 and mu n that is 5.05 into 10 to the power minus 27 joule T inverse, and the value of applied magnetic field B naught that is 1.5 Tesla. So that will give rise to 4.23 into 10 to the power minus 26 joule. And since the and again the daily value is extremely small, and since daily by kt is very small, e to the power kt may be approximate to 1, and thus the ratio of the nuclear spin population on the two energy states will be like this. So here the ratio will be 1 minus 4.23. This one means this the value is minus del E by kt. So here, as the value of minus del E by kt is small, e to the power minus del E by kt can be written as 1 minus del E by kt. So here we can find out 1 minus del E by kt, that is equal to 0.9999898. Since the transition from lower state to upper state involves absorption of radiation and that of the higher state to the lower state, the emission of radiation. And if the nucleus will undergo transition from lower state to upper state, that will occurs by absorption of radiation of frequency from radio frequency region. And if the nucleus will undergo transition from higher to lower state, that will emit radiation that will fall in the radio frequency region. No absorption occurs unless lower energy levels have excess of protons. In this experiment, in the examples above, it is found that the lower energy level has about 2 excess of spins for every 10 to the power 5 spins in the upper level. So from this ratio, we can know that if total number if total number of nucleus at the lower energy level is 10 to the power 5, then the total number of nucleus at the higher energy level will become 9999898. That means just only 2 excess of spins will be there at the lower energy level. So as the energy is very less, it is observed that almost same number of nucleus will occupy the lower and higher energy level. Only the lower energy level 2 excess of spins will be there. Now coming to Larmor precession. So Larmor precession, in order to understand the phenomenon of Larmor precession, we should recall the behavior of a spinning top. Spinning top means that is called as gyroscope. The spinning top executes two simultaneous motions. So you can consider this is a spinning top. This one is a spinning top just like a cone. So that is called spinning top. So the spinning top possesses two simultaneous motion. The first motion is it spins on its axis as well as around its own axis. So the spinning top will spin. So this is its axis, and simultaneously that will rotate around its own axis. That will follow. So the spinning top will follow this axis, and simultaneously when that will spin, that will also spin around its own axis. So two types of motions are there for spinning top. It spins on its axis as well as around its own axis. The motion around vertical axis arises due to interaction of spin, that is gyroscopic motion of the earth gravity acting vertically downward. This motion is called precessional motion. And the spinning top is said to be precessing around the vertical axis of the earth gravitational field as shown in the figure. So this type of motion, that is called precessional motion. That means the spinning top will undergo motion around its own axis, as well as around its own axis. So a spinning top, if you consider a spinning nucleus, that is a motion. When so if you consider the spinning nucleus, that is a proton, that is 1h1 as as a spinning top. So when placed in external magnetic field, also exhibit precessional motion. A spinning nucleus under the presence of external magnetic field can precess around the axis of an external magnetic field in two ways. It can either align with the field, so if that will align with the field, that will possess lower energy state, or it can oppose the field direction, that will possess higher energy state, and typically shown in this figure. Now let this one is the proton 1h1 having one proton. So if that will and this is the external applied magnetic field B naught. With reference to the external applied magnetic field, the spinning top will precess around the external magnetic field like this. So if that will precess around the external magnetic field, as well as that will precess around its own axis. So if the with reference to the external magnetic field, if that will precess around its own axis in the same direction, that is in the clockwise direction, this is the clockwise direction, then that will align with the external magnetic field and that possesses lower energy. And here, with reference to the external magnetic field, the proton will precess around the axis of the external magnetic field, as well as if that will precess around its own axis in anti-clockwise direction. So this is the direction of precession around the axis of external magnetic field. But if that will precess around its own axis in anti-clockwise direction, then that is called opposed and having higher energy. So the energy difference between the low energy and high energy state daily equals to h nu. The precessional frequency omega is called Larmor frequency and directly proportional to the strength of the external magnetic field. So the precessional frequency of the proton omega is directly proportional to B naught, and omega equals to some constant gamma into B naught. Here gamma is called gyromagnetic ratio or magnetogyric ratio. Either you can tell gyromagnetic ratio or magnetogyric ratio. It is the ratio of the nuclear magnetic moment mu and nuclear angular moment I. So gamma equals to mu by I, and the normal frequency nu is the precessional frequency omega. So this is the linear frequency nu, and for precessional frequency omega, the relationship between nu and omega equals to 2 pi nu, so which is equals to gamma B naught. Now we can write, because here we find that omega equals to gamma B naught, and here we find that omega equals to 2 pi nu. So nu is the normal frequency, and here the precessional frequency, that is omega. So omega equals to 2 pi nu, and from this equation omega equals to gamma B naught. So 2 pi nu equals to gamma B naught, and from this we can calculate nu equals to gamma B naught by 2 pi. So which is equals to B naught by 2 pi into gamma by I. B naught by 2 pi into mu by I, because we can put the value of gamma equals to mu by I, and after substituting the value of I and mu in from equation 1 and 2, we can write nu equals to Gn mu n, nu equals to Gn mu n B naught by H. Now coming to magnetic resonance. Experimentally, there are two different ways to achieve the resonance. So here we will discuss what is resonance. To understand this, let us having the equation 12.5 again. So the 12.5 says nu equals to Gn mu n B naught by H. So this equation shows that there are two variable parameters. So in this equation there are two variable parameters. So the variable parameters, the two variable parameters are this one variable parameter new, and the next variable parameter is B naught. And for a particular proton 1H1, Gn, mu n and H all are constant. Gn, mu n, H being constant, one obvious way to achieve the resonance is to vary the frequency at a fixed magnetic strength. This technique is called frequency sweep method. In this method, the sample is placed between the two poles of a strong magnet. That means the magnetic field strength here it will be constant, right? So we can change the frequency, because from this equation we can see that these two are the variables nu and b naught. So two different methods are there. The first method, here we will put the value of b naught constant, that is put the value of magnetic field strength constant, and the technique is called frequency sweep method. In this method, the sample is placed between the poles of a strong magnet, which generates two energy levels and cause the nucleus to undergo precessional motion. And the sample is irradiated with variable radio frequency generated by an oscillator and transmitter, and then that will undergo resonance. The resonance condition is achieved when the frequency of the radio frequency radiation matches with the Larmor frequency. Under this condition, that is called resonance. That means when the frequency nu matches with the Larmor frequency, frequency nu means frequency of the electromagnetic radiation irradiated to the sample. That is matches equals to omega Larmor frequency. Under that condition, the nucleus is said to be in resonance. The nuclei in the lower spin state absorb the radiation and go over the higher spin state. And again that will come back from the higher spin state to the lower spin state by emitting the radiation. And that condition is called as spin flip. So the spin flip condition will be achieved when the nucleus is in resonance. So the resonance condition will come when the frequency of the electromagnetic radiation is radiated to the sample will be equals to nu omega. When nu equals to omega, that is called resonance condition. So at the resonance condition, the nucleus will undergo flipping between higher to lower and lower to higher. So that is called flipping, and that is called spin flip. So when spin flip, when in the lower, that is parallel spin, higher anti-parallel spin. So during flipping, the spin of the nucleus will continuously change. We can keep the oscillator frequency constant, and the second method, we can keep the frequency constant, that means the nu constant, and we will change the value of the external applied magnetic field B naught. This technique is called field sweep method. The first technique was called frequency sweep method. That means the frequency value will be changed and then flipping will occur. And similarly, the second method, where the oscillation frequency will be constant, that is nu will be constant, and only we will change the value of the external applied magnetic field B naught. When field strength is low, the precessional frequency is lower than applied radio frequency, and since the two frequencies do not match, no energy is absorbed. As we increase the field, the precessional frequency starts to increase. So initially, as the field is zero, initially as the field will be lower, the frequency will be high. Frequency means new value will be high, and the value of the omega will be low because B naught will be low. And when we will increase the value of B naught, the value of omega will be increased. And when the value of omega will be equal to the value of nu, which is constant, at that condition, so resonance will be there. And during resonance, the nucleus will undergo flipping. That means energy will be absorbed. So when energy will be absorbed, the nucleus present at low spin state will move to high spin state. and again that will come to the low spin state. So as you increase the field, the precessional frequency starts increasing, and at a certain field strength, it matches exactly with the applied radio frequency, and the resonance condition is achieved, and radiation is observed. So when radiation will be observed, this cause transition from the alpha to beta state, and in common instrument, both the methods are used. That means both the frequency sweep method and field sweep methods are used. However, the field sweep method is preferred. Field sweep method means we have to fix the radio frequency region. Only we will change the value of the applied magnetic field V naught. It is because of the relative ease of varying the field. The field sweep method, continuous variation of the magnetic field strength is achieved with the help of a special coil present in the poles of the magnet. So in the field sweep method, we have to continuously vary the applied field strength, so that at a particular condition, at a particular applied field strength, resonance will occur. When resonance will occur, the nucleus will undergo flipping. In both the setups, In both the setups, the different protons are brought into resonance only one by continuously varying either the field or the frequency. Therefore, this is called continuous wave spectrometry. The CW method, continuous wave spectrometry, the CW method was the basis of all NMR instruments constructed up to the above end of the 1960. So up to 1960, the basic principle of NMR instrument was CW method. Those CW method still in used some lower resolution instrument, but in the modern instrument, that is FT NMR technique, that is Fourier transform NMR technique. So in the Fourier transform NMR technique, the spectra do not matter whether the NMR spectrum is recorded by CW or by FT technique. So we will discuss the FT technique later. So first, we will discuss here the principles. In the principle, we will find the relaxation mechanism. In the previous sections, we have learned that the population of the energy levels is governed by Boltzmann distribution law. Once a radiation is observed, then population distribution get disrupted. So before the application of the external magnetic field or before the irradiation of the sample through radio frequency region, according to the Boltzmann distribution, the different nucleus will be present in different energy levels. Once radiation is observed, the population distribution get disturbed. So all the population difference between the two spin states is very small. As the population difference between the two spin states is very small, the population of the lower and higher levels would become equal after the absorption of radiation sometime. So sometimes after absorption, because from the Boltzmann distribution law in the previous section we know that for 10,000 10 to the power 5 number of, if 10 to the power 5 number of samples will be present at the lower energy state, then 99,998 sample will be present at the higher energy state. Just two protons will be lesser than just two less protons will be present in the higher energy state than the lower energy state. But when the sample will undergo to radio frequency region, if they will observe, once the radiation is observed, the population get disturbed. As the population difference between the two spin states is very small, the population of lower and higher energy level will become equal after absorption of radiation for some times. After absorption of radiation from radio frequency region, at a, for sometimes you will observe that the population of the lower and higher energy state will be same. It means that resonance signal has achieved and saturation will be there and no more energy can be observed. However, There are some competing phenomena do not allow this stage to come. This competing phenomenon is called as the relaxation mechanism. The process of relaxation, the nuclear spin in the excited state relax down to the lower state to through radiationless process. So that means when the number of nucleus in the lower and higher energy state will be same, then resonance will be achieved. Resonance will be achieved according to the theory. No more resonance, no more energy will be absorbed. But this situation will not come. Why this situation will not come? That is according to that can be explained according to the relaxation mechanism. Now, according to the relaxation mechanism, the process of relaxation, in the process of relaxation, the nuclear spins in the excited state relax down to the lower state through radiation-less process. That means the nuclear spin in the process of relaxation, the nuclear spin in the excited state relax down to the lower state through radiation-less process. That means without emitting radiation, just emitting heat or any other form of energy, that will undergo the nucleus will undergo relaxation from higher energy state to lower energy state. There are two type of relaxation processes. One is spin lattice relaxation and another one is spin relaxation. First, we'll discuss about the spin lattice relaxation. This process involves transfer of energy from the nucleus spin in the higher energy state to the molecular lattice. So the random motion of the adjacent nucleus. So that means, so here the nucleus at the high energy state will come back to the lower energy state by transferring energy to the molecular lattice. That is called spin lattice relaxation. And in spin relaxation, this mechanism of relaxation involves mutual exchange of spins by two precessing nuclei to the close proximity with each other. For example, if there are two nuclei, one of these can flip down to other may flip up, then by mutual exchange of spins, that is also called as transfer, that is also called transfer relaxation. So that is called, so that means one nucleus at high energy state will transfer its energy to another nucleus which is at low energy state. That is called spin relaxation. Now coming to nuclei other than proton. So all this theory discussed now, up to now, all this theory discussed that belonging to the proton NMR, that is 1H1. So that is for one proton will be there, that is called PNMR. And similarly, other nuclei also nuclear NMR active. Those nuclei show NMR that have nuclear spin angular momentum I is greater than equals to half. More than 200 isotopes in principle can be studied by NMR, but according to our widely used techniques, 6 carbon 13, 9 fluorine 19, and 15 phosphorus 31 are most widely used besides 1H1. So 1H1 is the major technique apart from PNMR, that is 1H1 NMR, that is called proton NMR, PNMR. The other NMR techniques are carbon NMR, fluorine NMR, phosphorus NMR. So for carbon NMR, 6 carbon 13 nucleus are used. For fluorine NMR, 9 fluorine 19 nucleus are used, and for phosphorus NMR, 15 P31 nucleus are used. So the characteristics of the nuclei are given in table number 12.1. In many organic compounds where proton magnetic resonance spectrum PNMR does not provide ambiguous information. So in if any organic compound PNMR does not provide any type of structural information, then we can undergo CNMR or carbon 13 NMR that have been found especially useful for structural elucidation. Carbon 13 NMR spectra are intrinsically much less sensitive than proton NMR. So the low signal strength from that fact that the natural abundance of, so that will show So the spectra for C13 NMR show low signal strength because the abundance of C13 is only 1.11% of the total carbon, and also the magnetic moment is 1 by 4 of that of the proton in a given magnetic field. So here you can see the different types of NMR used, the different types of nuclei used in NMR. First one is proton NMR. Here I equals to half, isotopic abundance that is 99.98, and here the gyromagnetic ratio value is there. Then the relative intensity, if its intensity is 100%, then its relative intensity is 1, and GN value, nuclear G factor value for PNMR, that is 5.585, and observance frequency at 4.7 Tesla external magnetic field, that will observe at 200. Observance frequency is 200 megahertz. And if you use carbon 13 NMR, its spin value I value equals to half. Its abundance is, so the abundance of proton NMR is 99.98%, but for carbon NMR that is 1.11%, and here the gyromagnetic ratio is this. Then if its intensity for the proton NMR will be 100%, then for carbon 13 NMR its intensity will be 2%, and here its GN value and the absorption frequency value. Then for 19 F19, it's abundant in 100%, but relative in, if the intensity of the proton NMR for the sample will be 100%, then the fluorine NMR that will show 83%. And similarly for phosphorus 15P31, here the value of I is half, and isotopic abundance is 100%. Gyromagnetic ratio value, so this is the gyromagnetic ratio, is the relative intensity of what proton NMR for a particular sample is 100%. Then for fluorine NMR, then for phosphorus NMR it will be 7% only. Besides carbon 13, two other most widely investigated nuclei are fluorine 19 and phosphorus 31, both which not only have I equals to half, but both of these nuclei have natural abundance around 100%. So in this case, the NMR spectra can be analyzed in terms of their characteristics, chemical shift, spin coupling, etc. So now we'll discuss about the chemical shift. So that is a very important factor, chemical shift. In describing the behavior of nuclei in the presence of magnetic field discussed so far. So what we have discussed, the magnetic field discussed so far holds good only for bare nuclei. The resonance condition for such nuclei will, so for bare nuclei, when magnetic field will be applied, then the resonance condition for such nuclei, nu equals to Gn mu1 B naught by H. So this is the condition where the resonance will occur. It implies that all the nuclei of a given type in a sample should absorb the energy corresponding to the above nu value. If this was the case, then the NMR spectroscopy would have been no use to the chemist. In system, we do not deal with bare nuclei. The nuclei are surrounded by electrons, because all those things we have discussed, that is for bare nuclei. That means we have neglected the presence of electrons around the nucleus. So, but in actual cases, the nuclei are surrounded by electrons, and their presence can modify the field experienced by the nuclei either by shielding or de-shielding. So this makes the nuclei to come resonance at a different frequency. To understand this, so first we'll discuss the induced magnetic field. So the electrons circulating around the nucleus, because all the theories we have discussed, that is for bare nuclei. All the theory in the previous sections we have discussed, that is for bare nuclei. But in actual case, in any type of nucleus, electrons are surrounded by the nucleus. So the presence of electron will be there. So due to the presence of electron, when external magnetic field will be there, the electrons present around the nucleus will either shield the nucleus or de-shield the nucleus. So the two factors we will understand here. So the electrons circulating around the nucleus in a spherical fashion produce induced magnetic field B induced. When external magnetic field will be there, when external magnetic field will applied in case of hydrogen atom, then the electron present around the nucleus of every hydrogen atom so produced induced magnetic field, which opposes the applied magnetic field B naught. Therefore, the magnetic field experienced by the proton in a molecule placed in a magnetic field strength B naught is always less because of the shielding or screening of the nucleus by the surrounding electron. So this effective magnetic field experienced by the nucleus, because the applied magnetic field is B naught, but due to presence of electrons around the nucleus, the electrons will induce some additional magnetic field which are opposite to the field of the applied magnetic field, and that is called as B induced. So, although the applied magnetic field is B naught, but the effective magnetic field for the nucleus, that means the experienced field strength by the nucleus, that is called B effective. So, B effective is equals to B naught minus B induced. In order to find out the value of B effective, we should know that what is the value of B induced. B induced is directly proportional to B naught. So B induced equals to sigma B naught, where sigma is called shielding constant, and that is a measure of extent of shielding by the nucleus by the electrons. Substituting the value of B induced in this equation, we can write B effective equals to B naught minus B induced, or B effective equals to B naught minus sigma B naught. If we take common B naught, so which is equals to B naught whole into 1 minus sigma. The presence of extra nuclear electronic environment, the resonance condition get modified. So nu equals to, in the previous formula, the frequency nu equals to Gn mu n B naught by H, but in actual case, the experienced magnetic field by the nucleus is not B naught, but the value is B naught whole into 1 minus sigma. So by putting the value of the experienced magnetic field by the nucleus, we can write nu equals to Gn mu n B naught into 1 minus sigma by H. So that means in place of B naught, here we are putting the value of B effective. And the value of B effective is B naught whole into 1 minus sigma. So here we will take just 2-3 minutes gap, and after that again we will start. Stay here. Okay, so we'll start now. So here we have modified that. So if we'll use bare nucleus, then the value of nu equals to Gn mu n B naught H. But in actual case, the nucleus which is under irradiation with radio frequency wave, they contains electrons circulating around it, and hence the field, although the field strength is B naught, but due to shielding or de-shielding effect, the effective field strength by the nucleus is B effective, which is equal to B naught whole into 1 minus sigma, where sigma is the shielding constant. And putting the value of B naught whole into 1 minus sigma in place of B naught, we can write nu equals to Gn mu n B naught whole into 1 minus sigma divided by H. So, in molecular systems containing nuclei other than that of hydrogen and pi conjugated system, the field generated by the electron may augment the applied field. So, this is the effective field. This is the effective field at the nucleus may more than the applied field. So, where the for molecular system containing nucleus other than hydrogen, so if any type of molecular system other than hydrogen will be there or pi conjugated electrons will be there, then in that case the B effective will be increased. So the value of sigma, and as the value of B effective will be more than the value of B naught, the value of sigma must be negative. So 1 minus sigma, that will become positive, and the sigma will be negative. In such cases, we say that the nucleus is de-shielded. And if the nucleus will be shielded, the value of sigma will be positive, and hence the B effective will be less than B naught. And in case of de-shielding, if the nucleus will be de-shielded, then the value of sigma will be negative. In that case, B effective is more than B naught. So when shielding occurs, B effective is less than B naught, hence B naught must be increased in order to bring the nuclear resonance. On the other hand, when de-shielding occurs, B effective is more than B naught and requiring the field to be reduced to achieve the resonance. Thus, the nucleus come in the resonance at lower field. Therefore, due to shielding or de-shielding, identical nuclei which have the different chemical environments, in other words, with different electron density, resonate at different values of the frequencies or applied field. So these values bring the characteristics of the chemical environment can be used to identify various type of environment in which the proton is present. Since the shift in the position of the resonance is due to difference in the chemical environment, that is called chemical shift. Now let us first learn the shielding and de-shielding mechanism. First we'll discuss the shielding. The magnitude of the chemical shift is proportional to strength of the magnetic field generated by circulating. The magnitude of the chemical shift is proportional to the strength of the magnetic field generated by the circulation of surrounding electron about the proton. In order to understand the chemical shift value originating from the structural arrangement, it is essential to understand the nature of this electron circulating and corresponding induced magnetic field. The proton experience shielding due to combination of different type of electronic condition. So now let us explain that one. In which case the proton will experience shielding. It may be noted that the electronic distribution for a free hydrogen atom or hydride ion are spherically symmetrical. So this is the, and the applied magnetic field induces the electronic circulation around the nucleus in a plane perpendicular to the applied field. So if this is the direction of applied magnetic field, then the electron present in hydrogen or hydride ion, so that will undergo circulation around its. So this is the nucleus, and these are the circulating electrons around the hydrogen or hydride ion nucleus, and that will generate external. So when a charged particle will undergo acceleration, that will induced magnetic field in that case. So this is the applied magnetic field, and here induced magnetic field is in the same direction as that of the applied magnetic field. So this generate a small magnetic field in which the neighborhood nucleus is opposed the direction of the applied magnetic field as shown in this figure. So this is called diamagnetic effect and cause resonance to be observed as high field. So here, we can observe, so that is opposed. That is called diamagnetic effect. In original, in organic molecules where the hydrogen is bound to carbon and other atoms, the electron distribution is spherical, is not spherical, and so here we have considered only for single hydrogen atom or hydride ion. Here the electron distribution is symmetrical, and that will oppose the external magnetic field. But in organic molecules where hydrogen is bonded to carbon and other atoms, then the electron distribution is not spherical as in the above case, and the electron occupy p and d orbitals in addition to spherical s orbital. For hydrogen or hydride ion, all the electrons are present in s orbital, so spherical distribution of electron density was there. But in other organic molecules where hydrogen atom bonded to carbon and other atoms, then the electrons then the electron distribution are not spherical. So the electrons occupy p and d orbitals apart from the s orbital. In case of two types of effects, so in that case two types of effects are generated. So there are a diamagnetic effect in which the induced magnetic field direction is opposed to the applied magnetic field and shields the nucleus. The other kind of effect is paramagnetic effect, which arises due to induced magnetic field whose direction is parallel to the applied magnetic field. In that case, de-shielding effect is there. Now coming to the standard for chemical shift. So in case of organic compounds, generally tetramethyl So this is silicon. Four methyl groups will be attached to that silicon atom. So silane is SiH4 and tetramethylsilane is CH3 whole 4. That means all the four hydrogen atoms will be replaced by four methyl groups. That is called tetramethylsilane. So the four hydrogen atoms will be replaced by four methyl groups. That is tetramethylsilane. So for tetramethylsilane, that is called TMS, is used as a standard with respect to in which the chemical shift data is reported. So in order to calculate the chemical shift of any type of organic molecule, it will compare with the with tetramethylsilane, where tetramethylsilane will be considered as the standard. So the TMS has the following characteristics that make a molecule choice to act as a reference. So why the TMS acts as the reference? Why the TMS acts as the reference? So these are the following characteristics possessed by TMS. That's why it acts as a reference. First one, it gives a strong and sharp signal at a very high field. First one, it gives strong and sharp signal at very high field. Therefore, it does not interfere with the signal of all other type of protons in different organic molecules as they observe at lower field with reference to TMS. So the first one, so the question is why TMS is chosen as a standard. The first one is it gives a strong and sharp signal at a very high field, and due to this, it does not interfere with the signal of all other type of protons of different organic molecules as they observe lower field with respect to TMS. The second one is all the 12 protons present in TMS are chemically and magnetically equivalent. Therefore, this gives a reasonably intense signal at very low concentration also. Here 12 protons are there. In TMS, 12 protons are there. All the 12 protons are chemical and magnetically equivalent, and hence they will show intense signal even at very low concentration. And the third one, it has low boiling point around 27 degrees Celsius and is soluble in most of the organic solvent. Hence, it can be easily removed or separated from other organic compounds as the solvent after the spectrum is recorded. So the boiling point of TMS is low, that is 27 degrees Celsius. So after the spectrum is recorded, if you
Ketera?
want to move
Ih,
the TMS,
sotro.
then you can boil
Galpola.
more than 20.
Galpola.
And the fourth one, it is highly inert, does not interact with most of the organic compounds, hence it does not interfere the NMR measurement of any type of organic compound. So these are the four reasons for why TMS is chosen as a reference molecule for NMR measurement. Now coming to units of chemical shift. So here the chemical shift of any type of organic molecule will be recorded with reference to TMS. In the spectrum, in the NMR spectrum, the x-axis of the spectrum refers to energy of the electromagnetic radiation in terms of wavelength, frequency, or wave number. In case of NMR, the x-axis should be the frequency of the radiation being absorbed or the field at which the resonance is achieved, that is fixed at a particular fixed radio frequency. In any type of spectrum, we have studied in the earlier classes that the x-axis corresponds to the wavelength frequency or wave number, but in case of NMR, here the x-axis will be frequency of radiation being absorbed by the sample at a particular field, or the field strength of the sample at a particular predetermined radio frequency. However, using the frequency or the field is quite inconvenient. So since the frequency of the observed depends upon the applied field strength, the position of the signal of any type of given analyte will depend upon the applied field. So that is the position of the signal obtained by given analyte at different instrument will be different. So that's why the position. So if the instrument will be different, you will observe different position of a particular analyte. Therefore, we need a parameter that is independent of the applied field. So it will vary the you will undergo NMR spectra different instrument depending upon that field strength. You will observe that the peaks, the position of the same analyte will be different at different instrument. So in order to rectify that, we need a parameter that is independent of applied field. Such a parameter is called delta or ppm, which is dimensionless quantity. So that parameter is delta or ppm, which is dimensionless quantity. Let us try to understand the meaning of delta. Suppose we measure a test sample and the reference is TMS using the same magnetic field B naught. And the resonance condition for the two, we know that H nu test equals to Gn mu n B naught 1 into uh, Gn mu n B naught whole into 1 minus sigma test. So this is the test means the sample which will undergo resonance at a particular frequency. And the reference will undergo resonance at a frequency mu TMS. And hence H mu TMS equals to Gn mu and B naught whole into 1 minus sigma TMS. Thus, the shift of the resonance frequency will be to H nu test minus H nu TMS. So that is Gn mu and B naught whole into 1 minus sigma test minus Gn mu n B naught whole into 1 minus sigma TMS. And hence H whole into nu test minus nu TMS equals to Gn mu n B naught whole into 1 minus sigma test minus 1 minus sigma TMS. And hence this will 1 and 1 will be cancelled out, and you will find here that is, and sigma TMS is 0. Why that is 0? Because that is 12 protons are there. So the value of so reference, the chemical shift of the reference is considered to be 0. sigma TMS is 0, and we will find out the value new test minus new TMS equals to Gn mu and B naught whole into sigma minus of sigma test divided by H. Suppose we measure the same two sample test and TMS at double the field, then the shifting of the resonance will be new test minus new TMS will be 2 into Gn mu and B naught whole into minus sigma test divided by H. So the frequency difference between the test and reference gets double. Since the shift in resonance position is due to chemical environment that must be independent of the applied field, this can be achieved by dividing the shift in field or shift in frequency by the respective spectrophotometer of field or spectrophotometer of frequency, and hence the chemical shift equals to mu test minus mu TMS divided by mu OP. OP means operating frequency of the spectrophotometer. So this makes the shift is dimensionless. So the shift will become dimensionless, and but a problem still remains. The value of the ratio is very small because the shift in field or frequency is nearly 10 to the power 6 times smaller than that of the measured field or frequency. Therefore, we multiply this dimensionless quantity with 10 to the power 6 and express it in terms of parts per million, that is ppm. So delta equals to mu test minus mu TMS divided by new test minus new TMS divided by new OP, operating frequency, into 10 to the power minus 6, 10 to the power 6. So the delta scale ranges from 0 to 12 ppm. A high field of delta implies the signal to be downfield with reference to the TMS, and high field of signal will correspond to lower delta value. In order to circumvent this problem, another scale, tau scale is there. Tau equals to 10 to the power 10 minus delta. And here TMS is arbitrarily assigned a value of 10 tau. If we use delta, the TMS value is for TMS the delta value is 0. And if we use the tau scale for TMS the tau value is 10 tau. The unit is still in ppm with only difference in scale. So here this is the delta scale, delta H in ppm, and this is tau H in ppm. So this is increasing order of tau, and this is decreasing order of delta, and this is the increasing order of the field strength. So the typical chemical shift position of some commonly encountered functional groups. So this is the shift position of the reference, that is TMS. So nearer to that you will observe methyl, methylene, CH3, CH2, CH group, and if aromatic group is there, so the position will be around 2 point something, and similarly or halide you will observe more than 4. Similarly, if vinyl group is there, the TMS position, the position of sigma is around 6. And similarly, for aromatic hydrogen, the position is between 7 to 8. For aldehyde, the position is between 9 to 10. For carboxylic acid, the position is between 11 to 12. Now, factors affecting chemical shift. First one is electronegativity. So you know that the atoms of high electronegativity in the molecules draw the electron density towards itself. This causes a decrease in the electron density leading to deshielding of the nucleus. Thus, with increasing electronegativity, delta value will become high or go downfield. So here if hydrogen atom they are higher electronegativity, so the value of delta for CH3F is 4.24, and for CH3Cl that is 3.10, for CH3Br that is 2.26, for CH3I that is 2.1. So increasing the electronegativity of any attached atom, we will observe higher field. Then anisotropy of chemical bond. Chemical shift is dependent upon the orientation of the NMR active nucleus with respect to neighboring bonds, especially of the pi bonds. In such cases, the circular motion of the pi electron in presence of applied magnetic field generate induced magnetic field with anisotropic in nature. Anisotropy means that some part of the molecule or field opposes the applied field or other part augment with applied field. If some part of the molecule opposes the applied field and other part will align with the applied field, then that is called anisotropy. So here, so this is the shielding region, region for this type of molecule for carbonyl compound. So the carbonyl compound, the oxygen region, that is the shielding region, and the RC double bond R. So the carbon and alkyl regions are the de-shielded region. Let us understand this with the help of the example of a carbonyl group. The induced magnetic field is shown in this figure. There are two cone-shaped volumes lie parallel to the C double bond O axis. These are de-shielded regions, and any protons falling in this region would become resonance at low field or high value of delta. Low field means high value of delta. Higher chemical shift of the aldehyde proton is typically the example. And the protons that are outside the region of this cone will be shielded from the applied field and accordingly come to resonance at high field. Now, in case of alkynes or acetylenic proton, however, the protons appear in the upfield in the range of 1.5 or 3.5. So in this case, you can see that. So this is the C triple bond C, and here this is the acetylenic proton, the acetylenic proton. So that is you can see. So the paramagnetic effect on this proton, due to the paramagnetic effect on this proton, that will absorb at upfield. Upfield means lower value of sigma. So another factor is hydrogen bond. In case of hydrogen bonding, the hydrogen atom is shared by two electronegative atoms, so it is highly shielded, and the resonance occur at low field and corresponding high value of sigma is observed. Now coming to spin-spin coupling. Under low resolution, at low field, we generally get many signals in the NMR spectrum at different types of protons in the molecule. So the number of NMR spectra at low, so if we use the spectra at low resolution, the number of NMR signals equals to number of different types of protons present in the molecule. The ratio of intensity of the NMR signals are measured by the area of the peaks measured in the number of protons in each group. However, at high resolution, the spectral bands of a molecule containing non-equivalent protons are split into two or more components depending upon the nature of the neighboring group. The splitting of the signal is due to interaction of the nuclear spin of the adjacent nuclei, and the phenomenon causing such type of signal is called spin-spin coupling. The interaction or coupling of the spins is through the bonding electron. This effect is normally not observed if the coupled protons are more than 3 sigma bonds away. So here we will observe the spin-spin coupling for under the condition of low resolution. Ethyl chloride show two signals at its NMR spectrum. Ethyl chloride means one is CH2, CH3, CH2, Cl. If the resolution of the NMR will be low, you will observe that the molecule contains two types of protons. First one is for CH3, 3 protons, and the second type of signal will for 2 protons, right? So two types of signal in NMR will be observed, that is corresponding to CH3 group. One peak is for CH3 group and another peak is for CH2 group. The peak area are in the ratio 3:2 because here 3 protons are there and here 2 protons are there. The ratio of the peak will be 3:2. When same spectrum is recorded at high resolution spectrophotometer, the CH3 absorption band split into 3 lines, that is called a triplet, and the CH2 band split into 4 lines, that is called a quadret. So the CH3 absorption band will split into three lines, that is a triplet, and the CH2 absorption band that will split into four lines, that is called a quadruplet. This splitting can be explained in the terms of change in the magnetic field experienced by the protons in one group due to possible spin arrangement of the protons in the adjacent groups. Now let us focus our attention only in the methyl proton of the ethyl group. That means CH3 proton of the ethyl chloride. In the absence of neighboring methylenic group, so if this methylenic group will be absent, the methyl proton would come to resonance at a certain frequency depends upon the effective field strength experiences by them. So if this group will be absent, all the three protons will absorb at a certain frequency. It will give a singlet or single signal at low resolution spectrum. But in the presence of, but actually the CH2 group is there that contains two different protons. So due to the presence of a methylenic group that contains two equivalent protons, of the field experienced by the methyl protons get altered because the nuclear spin of the methyl protons also acts as bar magnet, and the magnitude of effect would depends upon the relative orientation of the nuclear spin of these protons. So the nuclear spin of the two protons can have four possible combinations. So the first one is, so the two protons, nuclear spin of the two proton means the two protons of the CH2 group. So the two protons, the first protons will oppose the magnetic field, the second proton will align with the magnetic field. Now both the proton may oppose the magnetic field. Both the proton, sorry, for the CH2 group, one condition is that the first proton will oppose magnetic field and second proton will align with magnetic field. So no shifting of energy will be there. And in second condition, the two protons either oppose magnetic field, either align with magnetic field, the energy will increase, and the two protons will oppose the external magnetic field, then the energy will be decreased. And in third condition, first proton aligned with external magnetic field, the second proton opposed with the external magnetic field. So this type of four combinations are possible. So in the first combination, both the spins are in alpha states. So this is the first combination, both the spin in alpha state. That means here we are considering the effect of CH2 group over the signal of CH3. First combination of the both the spins are in alpha state. As these are aligned with the direction of the applied field, the two that will align with the magnetic field experienced by methyl protons. As a consequence, the methyl proton will come to resonance at a lower field than in the absence of methylene proton. Similarly, the fourth combination, both the spins are in beta state, that will make the methyl group, make the CH3 group proton to come resonance at a higher field. And the two other combinations with alpha and beta, one alpha, one beta, would have no net effect of the methyl proton's absorption. Therefore, the resonance absorption signal of the methyl proton would be split up into three peaks. That is, so that will split into the NMR spectra of CH3 will split into three peaks with intensity 1 is to 2 is to 1. That will split into like this. Similarly, the fourth combination in which both the spins are in beta state, that will make the methyl group come closer at high speed. So therefore, the resonance absorption signal of the methyl proton would split into three peaks, that is a triplet, and having relative ratio 1 is to 2 is to 1. And if we will consider the multiplicity of CH2 due to the presence of CH3, that means three protons. So if three protons will either that if all the three protons will align, here all the three protons will be align means alpha and opposing means beta state. All the three protons are in alpha state, that is beta state. And second condition is 2 alpha 1 beta, so three possibilities are there. The third condition is 1 alpha, 2 beta. Again, three possibilities will be there. So the intensity of the signal for CH2 due to presence of CH3 at high resolution spectra will be split into a quadrate. The ratio of the quadrate will be 1 is to 3 is to 3 is to 1. 1 is to 3 is to 3 is to 1. Similarly, we can take other examples of molecule in which the given type of proton has one, two, three equivalent neighboring protons. In that case, we will find that the number of signals is governed by n plus L rule. If there will be one neighboring proton, that will split into doublet. If two neighboring proton, that will split into triplet. Or three neighboring proton, the signal will split into a quadrate. So that will govern by n plus 1 rule. In case of interacting nuclei, the relative intensity of the lines is in a multiplet is given by coefficient of the term by the expansion 1 plus x to the power n. This can be represented by Pascal's triangle. So so this is one. If there will be a doublet, the ratio will be 1 is to 1. For triplet, the ratio will be 1 is to 2 is to 1. For quadrate, the ratio will be 1 is to 3 is to 3 is to 1. For quintet, the ratio will be 1 is to 4 is to 6 is to 4 is to 1, and like this. So that can be explained. The intensity can be explained. The splitting pattern and intensity can be explained by Pascal's triangle. Now coming to magnitude of coupling constant. So different type of spin-spin couplings and their corresponding magnitude are there. So this is geminal coupling. That means splitting of this the NMR of this hydrogen atom due to this. So the value of J, that is coupling constant. The value of coupling constant J is around 10 to 18 depending upon the electronegativity of the attached group. And here this is called vicinal spin coupling constant due to vicinal protons. So here the two protons are attached to the neighboring hydrogen atom, depends upon the dihedral angle. So that depends upon this angle. Now, and here that is geminal proton, but attached to double bonded carbon. Its coupling constant value is 1 to 4, and this is vicinal proton attached to double bonded carbon with cis configuration, that is 5 to 14, and if trans configuration 11 to 19. And here this is the if this type of proton is there, its coupling constant 4 to 10. And for this, so these are the different coupling constants are there. Now coming to instrumentation of NMR. So the instrumentation of NMR contains a highly stable magnet, sample probe, source of radio frequency, and phase sensitive detector, data processing unit. So this is the schematic diagram of NMR spectrophotometer showing the various components. So here the sample is, so this is the sample tube. You can see that is the sample tube, and these are the high magnets are there. And here that is radio frequency oscillator. The sample is so radiated with the different radio frequency electromagnetic radiation. After that, that will undergo resonance, and that will be amplified to signal, and this is the output device. And so this is the typical representation of NMR. The NMR spectrum is recorded on a chart paper with x-axis representing the chemical shift. So in the NMR spectra, we can find out the x-axis will be delta, that is the chemical shift from right to left, and y-axis is the intensity. The delta value increases from right to left. The value of 0 on the x-axis corresponds to the internal standard, that is the TMS, tetramethylsilane. As we so that present at the right side. So this one you can see that is the TMS. At TMS the delta value is 0, and if you take a tau value, it is 10 tau. So the value of delta TMS will be 0. As we learned earlier, the lower delta value corresponds to high field and vice versa. So if we will go to lower delta value, so that is high field. Sorry, this one. Lower delta value means that is close to TMS, that is high field. The output consists of two traces. One is spectrum and the absorption signal at delta value, and other at integration trace. The integral trace gives the area under different peaks appears as state function superimposed on NMR spectra, typically showing in 12.19, and the internal tracing is usually recorded from left to right, and the height of the trace, internal tracing from left to right, and the height that traces arises with group proton is proportional to area enclosed by the peak, therefore to the number of protons responsible for the absorption. In general, NMR spectra can be classified into two broad groups: lower resolution NMR spectra, or that is called wide line spectra. Then high resolution NMR spectra, that is called sharp line spectrum. In a wide line spectrum, bandwidth of the line is large enough and fine structure due to chemical environment causing spin splitting is occur. And since the spectra is obtained from low field NMR spectrum, usually of less than 10 or 100 megahertz, and is useful for study the physical environment and observing species. Now, application of NMR spectra. So it has quantitative application. The quantitative application, the NMR spectrum has a unique feature of directly proportional between the peak area and the number of nuclei responsible for the peak. So that we have studied that. So the NMR spectrum has a uh, the peak area is directly proportional to the number of nuclei responsible for that peak. If the number of nuclei responsible for that peak will be increased, then the peak area will be increased. Unlike other spectroscopic techniques where calibration plot is prepared by using pure compound with varying concentrations, no pure sample is required for calibration in NMR. Thus, if an identifiable peak for one of the constituent of the sample does not overlap with with other constituent of peak, the area of this peak can be used to establish the concentration of species directly, provided that signal area per proton is known. And the signal area per proton, on the other hand, can be calculated using the known concentration of an internal standard. It may be emphasized that the peak of the internal standard should not overlap with the same peak. In this ground, organic silicon compounds are unique and calibrated for calibration purpose because high upfield location, that means the TMS. Now, analysis of multi-component mixture. A mixture of aspirin, phenacetin, and caffeine is a commercial analgesic preparation can be used by NMR with relative to error of 1 to 3%. Similarly, a mixture of benzene, heptane, and ethylene glycol and water can be precisely and rapidly determined by NMR spectra. Then elemental analysis. The NMR spectra are not routinely used for the determination of total elemental concentration at either, but in principle it could be used for given the NMR active nucleus in a sample. Then organic functional group analysis. A useful application of NMR in the determination of functional group of such hydroxyl groups in alcohols and phenols, aldehydes. So if you want to know the hydroxyl group in alcohol, phenol, or aldehyde, carboxylic acid, or olefinic hydroxyl group, or acetylenic hydroxyl group, or hydrogen amines, amides with respect to error of 1 to 5% range. Then qualitative analysis. So it is widely used in qualitative analysis. In qualitative analysis, we can find out it will help the structural elucidation of different types of organic molecules. So these are the applications So these are the NMR spectra of different types of compounds. You can see first one is the NMR spectra of ethanol. In the ethanol, you know that the compound contains three different types of protons. So it suggests that the presence of three protons of one type, that is CH3, and two protons of another type, that is CH2, and one proton of the third type, that is OH, right? Uh, so of course the OH proton is observed at the most downfield because it is attached to an electronegative oxygen atom, and one of the corresponding methyl group is observed at high. So this OH proton are the downfield, and this is at the upfield. CH3 at the upfield, OH proton is the downfield, and this is the peak for CH2. And similarly, you will observe the NMR spectrum. If you observe the splitting parameter, that means high resolution NMR spectra. This peak is for OH, this is for CH2, and this is for CH3. So this will give rise a singlet because that will form hydrogen bond with the sulfide, and the CH2, there are three neighboring protons are there, so that will give rise a quadrate, and for CH3 two neighboring protons are there, so that will give rise a triplet. Similarly, for methanol, if you observe the NMR spectra of methanol are different temperatures. So this is for methanol, this is a TMH, this is for CH3 group, and this is OH group. And if so, this is the observation of NMR at 36 degrees Celsius. At 6 degrees Celsius, we will observe that the OH group will shifted into higher and higher field. So this is the NMR spectra of benzyl alcohol C6H5CH2OH. So here you can see ben, uh, so that is the NMR spectra of benzyl alcohol. In case of C6H5CH2OH, the OH signal is observed at quite upfield, and the benzyl group is at downfield with methylene group between the two. So this is for benzyl group, and this is for OH group. This is OH group, and between that methylene group will be there. Phenol, so similarly you can see many type of organic. The structural elucidation can be done for different types of organic compounds. So okay, so here we will stop.